kids, excited to start Unit 3? Me too. Here we go. Do you like my comic? Do notice that your homework seems to be all over the place. I apologize, sort of. That's just because I don't like the way our book orders the first topic. So I'm going to take a piece from each one of these sections, put it all together in this first lesson. And hopefully after we go through a couple of sections, you'll understand why. All right, so second order homogeneous or homogeneous, I think, linear differential equations. I don't really know the right way to pronounce that. But so what is a second order homogeneous linear differential equation? That's a mouthful, right? Well, firstly, this is not one. Gosh, I'm trying to get this thing out of the way. Sorry. This is not one. So I do want you to notice that it is second order, right? There's the second derivative. And then also it is linear because y and all its derivatives are only to the first power. I have these functions called coefficients in front of y double prime, y, and I also have a function, and I'm using t this time, but I could just as easily use x over on the right hand. That is a linear second order ordinary, because no partial derivatives, differential equation. An initial value problem for these requires both an initial condition, right? Like, oh, y sub 0 is equal to 4 when I solve, because when I solve a general differential equation, I'm going to get not only one c, but I'm going to get two c's, right? You're going to have two different constants when you solve a second order differential equations, 3 when you do a third order, and so on and so forth. So to solve for two c's, I need two pieces of information because I have a second order. So I also need the slope of your solution, right, at that same point. And do notice this is an initial value, not a boundary value. So we are only dealing with the same x. All right, so general, if I ask you to solve for general, you're going to have a C1 and C2. If I want a particular one, I have to give you not only an initial point, but an initial slope. The term over here on the right side of the equal sign, that's the non-homogeneous term. If that value is 0, then you have a homogeneous second order differential equation. And we're going to learn how to solve those first. And the reason we're going to learn how to solve that kind first is if we can solve the homogeneous one, it's more work and can be pretty annoying, but we know we can solve the corresponding non-homogeneous as long as we can solve the homogeneous first. So that's what we're gonna do today, is how do we solve different kinds of second order homogeneous differential equations. So again, just for emphasis sake, I want you to look at these. The first example is non-homogeneous again, because I've got this term on the right that is not 0. So it is non-homogeneous. This one is a homogeneous linear differential equation because I am equal to 0, but it is third order, so we will not be doing that this chapter. We will only be doing second order. Also, I want you to note that in both equations, I've got coefficients. I have a constant coefficient here, but a function in terms of x here, a function in terms of x here. In this one, I have a constant in front of the y triple prime, but then I have a function in terms of x, function in terms of x, constant in front of y. But it is still a homogeneous differential equation because I'm equal to 0. In this chapter, our coefficients not only will be homogeneous, not only will we be second order, our coefficients are all going to be constant. Okay, so I'm reducing our set of differential equations even further, right? Starting with second order, linear, homogeneous with constant coefficients. Okay, so that's all we're going to be working with now. So first I'm going to ask you, can you just look at this differential equation and conceptually find a solution? In other words, what second derivative can I add to the original solution and get zero? Well, whose functions do I eventually get opposite of each other, right? Where are they, right? How about sine? Isn't it true that if I take sine x, its first and second derivative, then add the second derivative to the original, I'll get zero, right? I think you can see that, right? Y prime is equal to cosine x. Y double prime is equal to negative sine x. And sure enough, if I add y double prime to y, I get zero. Wouldn't that be the same with cosine? It would. Further, if I claim this is one solution to that differential equation and this is another one, any linear combination of those two will also be solutions. And that is a theorem. Right? And if you doubt me, just check it out, right? Take the first derivative and second derivative of this one, and this is a linear combination along with some, right, multipliers, some scalar multipliers of y sub 1 and y sub 2. Let's do another one like that. How about what kind of function has the same derivative, right? So that when you take derivative, a second derivative, and subtract it times the original, you get zero. What could it be? What could it be? It could be naturally e, right? So why is that? How about that one? Aren't they the same, right? So y prime is equal to e to the t, y double prime is equal to e to the t. This time I'm using t's instead of x's, but hopefully you can see that if you add y double prime, and then subtract a y, you do indeed get zero. The same would happen with e to the negative t. Just check it out if you don't believe me. And then again, if this I claim y1 is one solution, y2 is another solution, by theorem, any linear combination of those of solutions would also be solutions. Okay. Now I do want you to notice that curiously, I have highlighted, pun intended, the coefficients up here in exponential land. And then I want you to kind of look up here for a second. Oh no, what's going on here? Let's go on. Look at this one. What if I ask you to verify? I'm going to give you a solution and verify that it is indeed a solution to the homogeneous linear differential equation. All right, so there's y double prime minus 9y is equal to 0. So I claim that this general solution, this is general because I've got, right, coefficient here, I claim that this general solution, this general equation is a solution to the differential equation. So I'm going to verify that. I'm going to take the first derivative. I'm going to take the second derivative. Then I'm going to take the second derivative and subtract 9 times the original. Okay, take a moment and look at that. Think you can see what's going on. That is going to give me 0. Wait a second. Again, look at those exponents up there in exponential land, 3 and negative 3. And then look at my original differential equation. Hey, what if I had this as my solution? Right? Still with the 3 and negative 3 up there. Is that still a solution? In other words, if I did y prime of this one, I would get what? Negative 15 e to the 3t plus 0, because that one's zeroed out. And if I did y double prime I'd get negative 45 e to the 3t. Would that be true that y double prime minus 9 of, not this one, sorry, minus 9 times this one would equal 0? Yep, yep. What about that one? Yep. So I can change my coefficients in front of those two e terms. My c1 and c2 can change. But if I keep that e to the 3t and e to the negative 3t, I still get a solution to that differential equation y double prime minus 9y equal to 0. Wait, there's just something nagging at the back of my brain. I feel like I'm almost time traveling. Time traveling back to Algebra 1? What? Wait a minute. Wait a minute. This looks an awful lot like an Algebra 1 quadratic. That's a homogeneous second order linear differential equation. If I claim that y equals e to the RT is a solution, check this math out. This is so exciting. I took the first derivative, see what I did there, see what I did there. I took the second derivative, see what I did there. And then I'm going to plug back into here, right? I'm going to take y double prime and put it here and multiply it times a, y prime right here and multiply it times b, y right here and multiply it times c, and look what I get. Look at that. Good F word. Yeah, you know it. You know it. Oh, what does this mean? This means that either, since I'm equal to 0 because it's homogeneous, either this factor or this factor are equal to what? Yeah, you see what's happening. What's true about e to the, though? Yes, snap. E to the never equals 0, right? This will never equal 0. So, really? Are you serious? Here in unit 3 of differential equations, I freaking am dealing with an algebra 1 quadratic and relating it back to relating it back to what? I forget. What am I going to get when I solve that, if I was to solve that quadratic? What would I be solving for? R, right? And what's R? The exponents in my solution. This is called a characteristic equation of the homogeneous second order linear differential equation. Notice it's second order, and I have as quadratic, second degree polynomial. Gee, I wonder what will happen when I get to third, fourth, fifth, sixth. So if I have a homogeneous differential equation, the characteristic with constant coefficients, the characteristic equation looks like this, looks like an algebra 1 quadratic that I can solve for R, and boom, 3 cases. I have 2 real roots, right, when I solve a quadratic, or I can get repeated real roots, right, or I can get complex conjugate roots. Each time, how many do I get? 2. Yes, even in this case, right, I get 2 real roots. I technically also get 2 roots here. They're just repeated. Remember, the discriminant can tell me this, right? Complex conjugates, there's 2 of them, right? They're just conjugates. And this is a degree 2 quadratic, which came from a second order differential equation. My goodness, math is beautiful. So here's a theorem. If the characteristic equation of the homogeneous differential equation has n distinct real roots, real, so I'm talking case 1. And notice I'm not limiting myself here to second order either. This is true for any order homogeneous differential equation. The general solution is a bunch of constants, e to the solutions to your polynomial. Up there in exponential land, multiplied times t. Oh my Lanta. Further, these n solutions that I get are linearly independent. That's a big language word in linear algebra. But all we need to care about is that what that means is I'll get solutions that are not just multiples of one another. Wow. So let's suppose, without just visualizing it or somebody asking you to verify, can you find the general solution here? Whoops, sorry. To find the general solution, step 1, get the characteristic equation, which means look at the coefficients. This is A and this is C, right? B is the coefficient of y prime, and there is no y prime. So my characteristic equation is 1r squared, technically minus 0r, or plus 0r, doesn't really matter, minus 9, right? Technically r to the 0 is equal to 0. Well, this is r squared minus 9 is equal to 0, which means r is equal to, shocker, plus or minus 3, which means that my solution then, characteristic equation 2, right? Solve. Step 3, write your solution. And my solution will be y is going to be equal to 1 constant e to the r1t plus another constant e to the r sub 2. And if you don't believe me, you take derivatives and plug them in here. Not saying this is the only solution, but it is one, and that's all I care about, right? And it is a general one. And so you give me more information, I'll be able to solve for the C's. Whoa. So what if I asked you this question? What if I said, find a differential equation whose general solution looks like this? What am I trying to test here? What do you think? Exactly. I'm trying to say, oh, can you figure out that this would be, right? What's this negative 1/2 was R1 and negative 2 was R2. So that means that my characteristic equation looked like what? R plus 1/2 and R plus 2 was equal to who? So that's R squared plus 5/2 R plus 1 is equal to 0. That's the characteristic equation. How do I go to the differential equation from that? That would mean 1 y double prime plus, right, 1 plus 5/2 who? Y prime plus 1? No, plus 1 times y. Right? Cool. All right, how about an initial value problem? Remember, if it's second order, an initial value problem needs to give me at the same x a point on the curve, at that very same x, the slope. By the way, what does this mean, right? At 0, 2, the slope is positive 3, right? Can you picture that? You better. All right, so what do I got going on here? So let's step 1, characteristic. So I have A, B, and C. So that's 1r squared plus 5r plus 6 is equal to 0. Algebra 1. Who knew that algebra 1 would come in so handy, right? So what do I have now? So what is my solution? So that was step 1 was the characteristic equation. Step 2 was do the algebra 1. Step 3 was write out the solution. Right? Y is equal to one coefficient e to the negative 3t and second coefficient e to the negative 2t. But this time I have a step 4, right? Step 4, deal with the initial value, right? So what do I have? I have 2 is equal to, and I'm going to put a 0 in here and here. So aren't I just going to get C1 plus C2? Uh-oh, that's one equation and two unknowns. What do I have to do? Oh, right. I need to go find y prime. But I think you can do that. I have confidence, right? Y prime is going to be negative 3 C1 e to the negative 3t minus 2 C2. You thought plus C was bad in BC, right? You're going to have so many C's. And then I'm going to plug in what? 3 this time, right? So I'm going to get 3 is equal to negative 3C1 minus 2C2. I trust that you can do this algebra 1, right? That is just going to be a system and with nice little integers, and you're going to get C1 is, what did I get? Sorry, I'm not writing it down. Right? I got negative 7 and 9, and the negative 7 went with the negative 3. Yeah, so that's C1. So I got negative 7 and C2, which went with this. Negative 2 was 9. So now step 5 is write my particular solution. Y is equal to negative 7 e to the negative 3t plus 9 e to the negative 2t. Oh, I feel so good about our progress. Sweet. All right. I have a feeling that I typed all this up. Did I? I'm be so mad at myself. Oh, right. Solution should be increasing, right? Around the 0.02 because my derivative is positive there. Sigh. I did type this all up. Ah, yay, there I go. Okay, so just to repeat, and a lot neater than I did it myself, there was when I solved for 2. Okay. Then I took the first derivative. Yep. There I did. Yeah, I did. Yep. That's what I got. Then I solved the system, and that's what I got. And I led with the positive. I feel so good about myself again. All right. Now, not only did we get y, the solution, if I needed, couldn't I remember, I was just given y prime plus 5, y double prime plus 5, y prime, 6y. I solved for y. But now that I've solved for y, if I needed, couldn't I get y prime and y double prime? Couldn't I do that? I mean, there's no need to because no one asked you to yet. But what if I asked you to use a derivative test to determine the coordinates of the absolute max. Now I think I went ahead and edited this because some of this number isn't exactly nice. So I think on the next slide, I went to just finding the x coordinate, but whatever, I'll show you that in a minute. So here is the solution. Here's the graph of the solution. That's what y equals 9 minus this 9e thing minus 7e thing. That's what that looks like. Do you see the initial condition 0, 2? I do. Do you see that the slope is positive there? And could you buy that that slope is 3? Cool. Do you see that you have a maximum and that it is the absolute max? Right? And could you tell it would be an absolute max? Can you tell from, right, the behavior of these functions? Right? You know what e to the with negative co things do, right? Oh, so I am sorry, but this is out of order. I didn't get my animations right, I guess, before I started. So here's me taking y prime. So use a derivative test to find the x coordinate of that absolute max. Okay. So I found y prime because I already had y by itself. I set y prime equal to 0. That's the first derivative test. I multiplied by, right, kind of hard to solve for t, so I multiplied by e to the 3t because I'm pretty clever, as well as divided by -3. So that reduced the value of these coefficients when I divided by -3. And then do you see what happened when I multiplied by e to the 3t there? I just got e to the 1, right? And then, of course, I'm multiplying this side by 0, so that never changes. And then I did algebra 1, or algebra 2, I guess, and I got t is equal to ln of 7/6, which is not an integer. It's approximately point something, I think, when I looked at the calculator. But if you don't have a calculator, this is what you would get, right? Then I took this number to the second derivative. I found the second derivative, which wasn't hard, right? Not hard to find the second derivative from here. And I plugged in the value that I got, ln 7/6, and I got a negative. And I could kind of, even without a calculator, I can tell that this is going to be negative, right? Can you? With a -63, and this is going to be super small, right? But I'm only adding 36, right? So that's going to be negative. What's true when you have a horizontal tangent and the second derivative is negative, meaning you're concave which way? Concave down. Don't you have a max? So the calculus only tells me that that's a relative or a local max. But again, with the behavior of the original function with what y is equal to, I know the end behaviors. I know that that is going to be the absolute max because there's only one candidate on the inside and there were no endpoints. ln 7/6, again, 0.15 something. Sorry that those animations were kind of out of order. So let's generalize about some solutions to the second order differential equation that is homogeneous with constant coefficients when I got non-repeating real roots. When R1 and R2 are negative, right? So I've got a negative situation. This is what I have, right? I have a graph that kind of looks like that. We are most interested in the limit as t goes to infinity. Remember, these are mathematical models, right? We're not interested in time going backwards. We're usually interested in what's happening to the model because it's rates of change as I go to infinity. For instance, COVID, right? Modeling the spread of COVID was a complicated second order differential equation. Don't you want to know when it's going to decrease to 0, right? So you can see that when R1 and R2 are negative, my limit is going to be 0. That's like the function I have here. When either or both R1 or R2 are positive, I could have some different situations. I could either go to negative infinity or positive infinity. That could be good or bad, good or bad depending upon what I'm modeling, right? So, depending upon who's stronger, I could go to positive or negative infinity here. Right, so do you see this one? I've got a negative leading coefficient here, and I've got an e to the 3/2, right? This one is e to the 1/2. Both of them were positive, but I had negative, right? So, but I can figure this out, what's going to happen, right? If I have both positive coefficients, values of r, and then I have a negative leading coefficient here, but a positive here, what's that going to do to my end behavior? When either one is 0, right, that makes it, that's super simple, right? It's also going to swoosh off, right, to either a positive or negative. Here I have to kind of think about who's going to balance off, who's going to be stronger as I go to infinity, right? All right, case 2. Remember, case 1 was when my characteristic equation had non-repeating real roots. What if I have repeated roots? So if the characteristic equation of the second order homogeneous linear differential equation with constant coefficients has repeated real roots, then your solution has that repeated root in it here and here, but one in your linear combination, one of them has to get multiplied by x to avoid you just having, right? Because otherwise, that's just 2c1 e to the rx, right? So you need that extra x or extra t to avoid, if you're in t's, to avoid linear dependence or them just being constant multiples of one another. This guy, Jean de Laurent de Lambert, I think Jean Laurent de Lambert, is somebody who kind of generalized this. Oops, sorry. So finding the general solution here, again, I'm looking for coefficients in front of y double prime, y prime, and y. So I get r squared minus 4r plus 4 is equal to 0, meaning that r minus 2 squared is equal to 0. So I do get 2 roots, but they are the same. R equals 2. Therefore, my solution is y is equal to c1 e to the 2x and c2 e to the 2x, but with an extra multiplier in there. And that seems like, man, that's just going to throw everything off. There's no way that can be so. How can you check? How can you check me? Right? You can check if take the first and second derivative and plug them back in here. I promise you're going to get, right? This is your solution, I promise. Now, what does that mean kind of graphically, right? So here is one solution. Oh, I changed to t's. Sorry. Here's one of the solutions when I had a particular, right? I solved for my C1 and my C2. Right, so again, here is the factor because my roots were repeating. So I had that. Then was it positive or negative? Anyway, so just looking at this graph, what happens graphically? Again, we're interested as t or x goes to infinity. They're the same. It's the same situation that I had when R1 did not equal R2, right? I'm going when I've got negative, going when they're both negative, I'm going off to infinity. And what this means, the important thing for us is this factor, right, was negligible as I went off to infinity, which is what I really want to know. I want to know, right, am I going to zero out, or am I going to approach 0, or am I going to swoosh? right? So the linear factor certainly has an effect. It doesn't have an effect on the fact whether I'm a solution or not. But as I go to infinity, it disappears because the exponential takes over, right? Takes over. What if they both equal 0? That would be kind of boring, wouldn't it? All right, case 3. Case 3. Look at this scenario as you're writing it down. This is the case 3, right? When I'm solving right, from algebra 1, I could get 2 non-repeating real roots, 2 repeating real roots, or complex conjugates. So if your characteristic equation comes up with complex conjugate roots, a plus or minus bi, then your general solution has sine and cosine in it. And e. What the hee-haw? So the real component of your complex conjugate is what goes up in exponential land. And the imaginary part of your complex conjugate goes inside the argument of sine and cosine. So if look at this here, finding the general solution for this second order homogeneous linear differential equation, I have 1, I have -6, and I have +25. So I turned it into my characteristic equation. That was step 1. That does not change. Get your characteristic equation. But I tried to factor this. It does not factor nicely. So what was my step 2? If I can't factor, Euler came up with how this works. Oh, Leonard. So I'm gonna show you some steps that you don't. I'm gonna go through steps, and you're not gonna have to do all of these. I went to the quadratic formula, right, with my a, b, and c. I got 3 plus or minus 4i, so a is 3 and b is 4. Let's suppose I don't know that formula. Let's suppose I'm just following my e to the, right? I just said, oh, okay, well, I'm going to put, right, this is R1 and R2, so I put R1 here, and I put R2 here. Well, I can break that up, right, because that's e to a sum, so I can break that up, can't I? And here comes Leonard. Look what happens when I break that up. So I get e to the 3t here and here, which means I can F word, good F word, factor it out. And then I get times e to the 4i and e to the negative 4i. But Leonard, good old Leonard, e to the it and e to the negative it, he proved, and it's not a difficult proof to follow, that that's what it equals. Cosine t plus I sine t and cosine t minus I sine t. So that's where the formula comes from, right? So I have cosine 4t and sine 4t. And I know there's a negative in there, but remember that's kind of taken care of with the constant situation, right? So you obviously don't have to go through this part that Leonard did for us. You can go right from here to here, as long as you know to put the A part up in exponential land and the B part down in sinusoidal land. So let's do some generalizations about those solutions. So now think about it. I want you to think about the graphs that I showed you before, right? The graphs that I showed you before all either, as you went to infinity, you had e to the negatives or e to the positives or e to a mixture of positives and negatives, right? So my end behavior was either going to approach 0 or go to infinity or negative infinity, right? unless r's were 0 and then I had constants. So think about the kind, what do you think is going to happen when my solution, because I have complex conjugates and because of Leonard, I not only have E, but I've got sines and cosines. Can you figure out what's going on? Look at this. If I ended up where, whoops, sorry, A is 0.1, not 1, just so my graph looked decent. Look what happens when I have E to the, right? So I have E2 positive, and then it's multiplying sine, a linear combination of sine or cosine, right? We call this oscillating, right? Because you're going back and forth, but it's a growing oscillation. That's bad if you're doing control systems on a helicopter, right? You don't want growing oscillation in your helicopter system. But look what happens when A is negative 0.1. When A was negative 0.1, look what happens over time as I approach infinity. Right? So this is called, what do you think? It's still oscillating, but it is decreasing oscillation. That is generally a good thing, right? Think calming down. Think spazzing out. Think calming down. Calming down, right? What do you think happens in this scenario when A is 0, right? I just have cosine 4t plus sine 4t. So I just have constant oscillation. Not as good as decreasing oscillation, but at least it's not going crazy, right? Okay. Pretty cool, pretty cool. So this kind of analysis of the graph thing is not part of your homework. Your homework is just do the grunt work, get those, right? Look at the characteristic equations, find out, what your solutions are, or what your exponential expressions are. If you have complex, get sine and cosine. That's all your homework is, right? And that's what they did in your book. Put them in different sections, put real, repeated, and complex in different sections, and I just kind of put them all together. So enjoy that, and I will see you in a couple of days.